All right, so let's take a look at the history and state. When we mean history, we mean the sequence of observations, actions, and rewards, this free tuple that's happening over time. And basically, we're going to have these three things, as we illustrated in the last section, occurring over multiple time steps all the way until time t. The only difference is at time t, we're not going to take a final action. The action that we took at t-1 will represent the final action that we're doing, and the environment will have a chance to report what is the reward and the state that we end up in after taking the final action. Okay, so this could be, for example, in the case of a robot or autonomous vehicle or some type of embodied agent that gets and receives information from the environment about what types of observations it gets to see. Okay, so what happens next, we can say, is dependent on the types of history that's encoded, right? So the history of at a particular time step is all of the information up to that particular time step. And based on everything up to this point, we are going to make a selection of a particular action from a set of actions. And then we're going to say the environment gets a chance to select from its large state space what types of observation and rewards it gets to give back to us. For example, in some type of deterministic system, the agent's actions dictate what the observations and the environment will happen, but that doesn't necessarily have to be the case. There are many times when there are things beyond the control of the agent that changes what happens, and therefore we can think of the environment as a stochastic variable, right? So we're going to then say that state is all this information that's going to be used to determine what's going to happen next. We can say that basically it's some type of function of the history. So we have the information that's all encoded at a particular time step. This is all the history that's encoded by what you see on the left-hand side here. And basically we have a chance to engineer this particular f function, which is going to result in the state of the next part that we're encoding. And the state itself is fairly general, so we need to break it down into three different types of information. The state of the environment, the state of what the agent is doing or representing, and the information state in general. So let's take a look at what these three things mean in turn. So to start with, let's take a look at the environment state, right? So the environment state is basically whatever the environment uses to calculate its private representation. And we're going to denote that with this variable s at a certain time step t, but denoting it with a subscript e for environment, right? So you can think of it as some type of encoding of what's going on in an environment after receiving an action from the agent, okay? So whatever data is the environment is using to pick, what the observed values that it's going to expose to the agent, and what type of reward value, if any, it's going to send back to the agent, okay? Now, in many cases, like I said, the environment state is not usually visible. There might be other things that are going on in the environment. For example, there could be multiple agents, for example, other humans or other robots taking place, or things that are outside of what the system can see, okay, that are part of the environmental state. And then all of this could be exposed through the observation to the agent. And even in the case where the entire state space may be visible, it might contain irrelevant information. That happens a lot for human perception, right? Even though we have a large field of vision, our neural cortex is only really trying to observe key changes in the environment, right? Like we're very sensitive to motion. We can only really focus in one part of our focused attention. So So our system is basically filtering out a lot of information that might be given to us through the environmental variable, but which the agent is going to discard, right? So on the flip side, we have the agent state, right? This box here, which is then basically the same thing as the state, but now we're going to represent it with a superscript A. And we're going to say this is our agent's internal representation of what's going on, right? It's going to represent what type of information that the agent is using to pick the next action. So, I mean, you can exactly contrast these two parts here. And for us, that means any information that when we design our reinforcement learning algorithm that the agent is executing is whatever information that it's going to use. So for example, even though the state of the environment may contain irrelevant information, we would discard that and just use a subset of that for the information used by the RL algorithm to determine what the next action is. Now, of course, it can be any function of history, as we talked about before. So it could contain other information that's not found in the environment, any encoding of information that's used by the agent to decide what to do, right? That might not be visible to the environment or to any other agents, right? In fact, we can think of other agents as part of the environment with respect to this particular agent that we're trying to engineer a reinforcement learning solution for. So let's now look at one very key property called the Markov property. A Markov property, or equivalently an information state or Markov state, basically says that all of the useful information from the history is all compressed at the current time step. So what we mean by that is that a certain state at a certain time step, st, we can say is Markov if and only if all of the information needed to predict the probability of being in another state at a future time step, let's say t plus 1, is completely the same as whether we're given just the previous state or the entire history, right? So basically, we can say that the future is independent of the past given the present, meaning that I can truncate all of the information from the history, throw this away, and just represent all of that by encoding it in this state, the current state at the time step. And that's going to help me, the only information that I need to predict what I'm going to do for subsequent time steps, right? So what it means is once the state information is known for S of t, the entire history is irrelevant. Everything is encapsulated in the data that ST has to predict what's going on in the future. So for example, even though I have a lot of memories and they represent the history, what's contained in my brain is basically the state information, which is going to predict how I'm going to behave in the future. So we can say, for example, the state is then a sufficient statistic of what we are going to do in the future. And this is important when we can make the environment state Markovian or Markov, right? So that we can compress everything in this particular state representation of the environment for the current time step, which is going to reflect all of the information, again, for this particular quality sign to help predict what's going to happen in the future. So it helps to try to make this a little bit more concrete. So let's take the case of training rats, laboratory rats, right? So a laboratory rat might need to press a switch to turn a light on or ring a bell, for example. And after doing that, might get some type of reward through this slit here. Could be some food or some penalty in terms of electric shock, okay? So let's say, the rat is trying to be trained and there's some actions it could take. If, for example, it could ring a bell, turn on the light, and ring a bell at 4 different time steps. And then it could receive some action as a result. some type of reward as a result. And in this case, maybe it gets a small electric shock. So it doesn't find that very enticing. So it might try a different sequence of information. So for example, it might ring a bell, turn on the light, ring a bell, then turn on another light, and then, oh, look, I got some cheese as a reward. That's great. I like cheese. Maybe I should try to do more things of the second sort to get more reward than of the first sort. But what happens if I'm faced with something like this? I get a light bulb, I turn on another light bulb, I ring a bell, and I turn on a light bulb. Then what do you think will happen? Well, there are lots of things that can happen, and I think we've already convinced ourselves that this type of discrete learning problem, or this learning problem in general, is not feasible unless we make some assumptions, right? So it's quite clear that if we think about the agent state, what type of representation is it using? A conjunctive learning algorithm or something of that sort might give a rise to different type of interpretation. So, for example, if it's the last 3 items in sequence, we could say, okay, the history allows us to discard things beyond 3 time steps so that we can see here that the second row and the third row contain the same items. So I would expect this question mark to be cheese, right? But what happens if it's the counts for the lights and the bells? Okay, for example, here we have an odd number of bells and lights and an odd number of bells and lights. So maybe I would expect to get shocked. Oh no, I certainly don't want that, right? But it could be even the complete sequence. And what we talked about in the feasibility of learning before is that we won't be able to exactly decide this because actually, even though we only have 2 outcomes, either electric shock or cheese, it could be any one of these. You know, it's really up to the researchers who are trying to train the rats to provide incentive to learn a proper function. So this gets us back to the idea of what's going on in the environment, right? We said that we might have a case where the environment is completely transparent to the agent, or a fully observable environment. So an example of that is something like the game of Go or a game of chess, where all the pieces on the board are clearly in their position, and there's no uncertainty about what the environment represents, right? So in this case, the agent directly observes the environmental state, right? So the observation is congruent between the agent and the environment. And we can model this as formally, that we're going to talk about in the post-lecture, a Markov decision process, or MVP. So probably the more common case is when we have partial observability, where in an environment, we only observe the environment indirectly and not the entire environment. So this is the case for many agents embodied in the real world, where the real world is quite complicated, and we only get a small portal of information, or view of the information that's going on in the environment. For example, a vacuum robot with LiDAR might have a local sensor like the LiDAR itself and get some range information, but it is not actually told its individual absolute location. It might try to compose what it sees in its local environment with the map that it has provided by a third-party application, and try to align itself, localize itself into the environment. Similarly, a trading agent only observes the current prices. It doesn't observe prices in other stock markets, although you could try to tell it that. It might not be able to observe other trades that are going on outside of its immediate environment. And similarly, in this case of Dota, the agent that's computer controlled is only seeing where it is itself. As well as some local context. The game environment might be represented by a lot of other things that are going on outside of the specific view that the agent sees, and needs to take action on the fact that it can only see part of the environment. So here, then we can say that the agent state is no longer the same as the environmental state, right? This happens in the real world just the same as in Dota here, where there are many things beyond the periphery of what we can see that are going on that represent the state of the environment that could eventually influence what happens to the agent. And formally, we can say this inserts two letters in front of partial observability. So we have now a partially observable Markov decision process, or POMDP for short. And the key part here is that the agent is going to have to construct its own state representation, just like in a fully observable environment, but has to decide what it wants to capture. So it might say, for example, I'm going to take the entire history and use that to compute the current history through a Markovian representation, where I only use the current time step. I compress all of the information from the history into the encoding of the current time step, right? And in this case, we might have some stochasticity, which means that, depending on the action that the agent is going to take, we might end up in a different state. It's not completely deterministic what happens, right? So although, the agent, like the vacuum robot with LiDAR, says, oh, I want to go turn around the corner, actuality is that even though it tries to move around the corner, the motor might break or the LiDAR might not be working exactly properly, and I end up in a slightly different state than I wanted to be in. So the probability of being in exit state where the environment says you're probably in state 1 or state 2 or state 3. So this is just any number of possible states where we can think of each state as a learning instance, right? Depends probabilistically on what type of action the agent took. Okay, and we actually already know in many cases, deep reinforcement learning uses this concept where we're going to take some type of neural network architecture and represent the state. So we've already learned something like an RNN, which basically says, well, I have the state representation of what I did last, which we can think of as our state neural network to neural network transition, okay, our theta HH, for example. And then we're going to add that together with the current observation at the time step. So if you recall the diagram, it looked a little bit like this. So we're getting some input representation. This would be our observations, right? Our OOT. And here would be our S of A of T minus 1. And then we would have our S of A of T. So this type of transition theta from HH or theta of XH would be equivalent to what we have here, right? So this would be our HO, our theta O, and this would be our theta S, okay? Just to make it clear what it would be in the recurrent structure, okay? And so we can construct this representation and send it through a sigmoid gate or any other type of nonlinearity, like a ReLU, and then we would be executing something in a deep reinforcement learning architecture to construct a state representation.